Welcome. This video will be a compilation of my 45 and my 36 minutes of Carfax videos, so no new facts will be mentioned. Let's begin. The Curve-Oldsmobile of 1901 was steered with a tiller, similar to a boat, rather than a steering wheel. Drivers pushed the tiller left to go right and right to go left, which felt natural to people familiar with boats, but confused everyone else. This backward steering was inherited from horse-drawn carriages where the tiller controlled which way the front axle pivoted. Steering wheels didn't become standard until several years later, when their advantages became obvious. The steering wheel allowed for finer control and required less physical space than the tiller. It also felt more intuitive to people who had never driven a boat. By 1908, tillers had almost completely disappeared from automobiles. Today, finding a tiller-steered car is extremely rare, and most are in museums. Wooden spoke wheels were standard on cars well into the 1920s. These wheels were beautiful, with typically 12 spokes radiating from a central hub like a wagon wheel. But they required constant maintenance that modern drivers would find exhausting. The wood would shrink in dry weather and swell when wet. Spokes would loosen and need tightening with a special wrench. Owners had to check spoke tension regularly to prevent wheels from collapsing. The wood also had to be protected from the elements. Varnish or paint helped, but the constant exposure to road spray, mud, and weather took a toll. Wire wheels replaced wooden wheels in the 1920s, using tension steel spokes that didn't require the constant maintenance of wood. Stamped steel wheels became common by the 1930s, finally ending the need for regular wheel maintenance altogether. The progression from wood to wire to steel happened surprisingly quickly once the alternatives became available. The brass era of automobiles, from roughly 1896 to 1915, got its name from the extensive brass fittings on cars of that period. Headlamps, side lamps, horn, radiator, and various trim pieces were made of brass. This wasn't purely decorative. Brass was relatively easy to work with, didn't rust like iron, and could be cast into complex shapes. It was a practical choice given the manufacturing technology of the time. However, brass tarnished quickly, turning from shiny gold to dull brown or green if not maintained. Owners spent considerable time polishing all this brass to keep their cars looking presentable. Special brass polish and soft cloths were essential supplies for any car owner. Polishing the brass on a large car could take hours. Some wealthy owners had servants whose job included keeping the car's brass polished. When nickel plating became affordable in the mid-1910s, it quickly replaced brass because it didn't tarnish. A nickel-plated fitting would stay shiny with minimal care. The transition from brass to nickel marked the end of the brass era and the beginning of a more modern aesthetic in automobiles. Today, brass-era cars are prized by collectors partly because of those beautiful brass fittings that require so much care. Chain drive was common on early cars, with the engine turning a chain that connected to the rear axle. Similar to a bicycle, the chain ran from a sprocket on the transmission to sprockets on each rear wheel. This was simple and easy to understand, which made it popular with early manufacturers who were still figuring out how to build automobiles. But chain drive had significant drawbacks. The chains were noisy, clanking and rattling as they turned. They required constant lubrication to prevent wear. Even with proper maintenance, chains stretched and wore out relatively quickly. Exposed chains could also be dangerous, catching clothing or fingers if you got too close. Some manufacturers enclosed the chains in metal covers, but this made maintenance more difficult. Shaft drive, using a drive shaft and differential, proved more reliable and became universal by 1920. The drive shaft was enclosed, quieter, required less maintenance, and lasted much longer than chains. The differential allowed the rear wheels to turn at different speeds when cornering, which chains couldn't easily accommodate. A few specialty vehicles used chain drive into the 1930s, but for mainstream automobiles, shaft drive was clearly superior. Detachable cylinder heads weren't common until the 1920s. Earlier engines had heads cast as part of the engine block in one piece. This made the engine simpler to manufacture initially, but it created enormous maintenance problems. If you needed to service the valves, replace a head gasket, or do any work inside the combustion chambers, you had to remove the entire engine from the car. This process could take days. The engine had to be disconnected from the transmission, all the cooling system hoses removed, the exhaust disconnected, and the engine physically lifted out of the car. Only then could you access the valves and combustion chambers. After completing the work, you had to reinstall the entire engine and reconnect everything. What should have been a simple maintenance job became a major undertaking. Detachable heads made maintenance much simpler. You could remove just the cylinder head, leaving the engine in the car. This turned a multi-day job into something that could be done in hours. But some manufacturers resisted the change for years, claiming one-piece construction was stronger and less likely to develop leaks. Eventually, the maintenance advantages of detachable heads won out, and by the late 1920s, they were nearly universal. Coach builders were companies that built custom bodies for car chassis. In the early decades of automobiles, many manufacturers sold just a chassis with engine and running gear. This wasn't the complete car, just the mechanical components. Wealthy customers would then commission a coach builder to create a custom body to their specifications. It was similar to buying a custom suit rather than one off the rack. The process could take months. The customer would meet with the coach builder to discuss exactly what they wanted: how many doors, what style of roof, what material for the interior. The coach builder would create drawings for approval. Once approved, craftsmen would build a body entirely by hand. Wood frames were shaped and assembled. Metal panels were formed and fitted. Interior trim was custom-made. Each body was unique, hand-built to the customer's requirements. No two were exactly alike. Even if two customers ordered similar designs, small differences in dimensions, materials, or details made each one individual. This meant that repair work was complicated. If you damaged a custom body, you couldn't just order replacement parts. Everything had to be custom-made again. The practice continued into the 1940s for the most expensive cars, though it became less common as manufacturers began offering more body styles. By the 1950s, full custom coach building was essentially dead for new cars, replaced by limited customization options from a manufacturer. Today, a handful of ultra-luxury manufacturers still offer limited coach-built bodies, but the golden age of coach building ended decades ago. Figoni E.T. Falaschi was a French coach-building firm famous for their aerodynamic designs in the 1930s. Giuseppe Figoni and Ovidio Falaschi created some of the most stunning automobiles ever built. Their bodies featured flowing curves that seemed to defy the limitations of metal. Covered rear wheels, teardrop shapes, and smooth surfaces characterized their work. They were years ahead of mainstream design. Their designs weren't just beautiful. They were actually aerodynamic at a time when most car designers didn't think about wind resistance. The flowing shapes and covered wheels reduced drag, improving top speed and fuel economy. Of course, these benefits were secondary to the stunning appearance. Figoni E.T. Falaschi bodies were rolling art, sculptures that happened to be functional vehicles. The bodies were typically built on high-performance French chassis like Delahaye, Talbot Lego, and Bugatti. A Figoni E.T. Falaschi body could cost as much as a chassis itself, doubling the price of an already expensive car. Only the wealthy could afford them. Production numbers were tiny, often just one or two examples of each design. Today, they're among the most valuable pre-war automobiles, selling for millions of dollars when they rarely come to market. The Brewster Coach Building Company in America built bodies for the wealthiest families. Brewster had been building horse-drawn carriages since 1810 and transitioned to automobile bodies in the early 1900s. They brought nearly a century of woodworking and metalworking expertise to automobile coach building. Their reputation for quality was impeccable. Brewster Town cars feature luxurious interiors with fine leather upholstery, exotic wood trim, and even silver or crystal flower vases. Some had glass partitions separating the chauffeur from passengers, with speaking tubes for communication. The chauffeur's compartment might be open or have a removable top, while passengers enjoyed a fully enclosed cabin. Heat and weather protection were for the passengers. The chauffeur was expected to endure the elements. Brewster bodies were known for conservative, elegant styling that emphasized quality over flash. They didn't follow fashion trends but maintained a timeless, dignified appearance. Brewster clients wanted their cars to project wealth and good taste without being ostentatious. The conservative styling meant Brewster body cars looked elegant for decades rather than becoming quickly dated. Brewster tried building complete cars under their own name in the 1920s, but couldn't compete with mass-produced vehicles. They returned to coach building but never regained their earlier prominence. The company closed in 1937, a victim of the Depression and changing market conditions. Today, Brewster body cars are prized by collectors for their exceptional quality and elegant styling. Shooting brakes were originally custom wagon bodies built on luxury car chassis for British aristocrats going hunting. The term shooting refers to hunting game birds. Brake was an old term for a wagon, so a shooting brake was literally a hunting wagon. The rear cargo area was designed to carry guns, hunting dogs, and dead game. These weren't crude utility vehicles. They were custom built on expensive chassis like Rolls-Royce or Bentley. The front seats offered luxury car comfort for the lord and his gamekeeper. The rear cargo area had custom fittings for securing guns and provisions. Often there were folding seats for additional passengers or beaters. Everything was designed to be both functional and befitting the owner's status. After World War II, some manufacturers offered shooting brake models as part of their regular lineup, though they were usually called estate cars or station wagons. Aston Martin, Bristol, and other British luxury makers built small numbers of shooting brakes through the 1960s. Today, the term describes any luxury wagon or estate car, though few modern buyers use them for hunting. The shooting brake has become a style rather than a function. Modern recreations occasionally appear, with coach builders converting luxury cars into wagons, but true shooting brakes are rare. The costs of custom coach work make them impractical except as marketing exercises or one-off projects for very wealthy individuals. The golden age of the shooting brake ended when station wagons became common and lost their association with wealthy sportsmen. Convertible tops were canvas stretched over a folding frame. Early tops were difficult to raise and lower, requiring multiple latches and considerable effort. You had to unlatch the top from the windshield frame, then manually push it back while trying to guide the folding frame mechanism. Getting it to fold properly required practice. Once folded, you had to secure it with straps or a cover to prevent it from flapping in the wind. These canvas tops leaked almost from new. Water would seep through the fabric, drip at seams, and pull in any slight depression in the material. After a few years, the canvas would become brittle and crack. Replacement tops were expensive and required skilled installation. In cold weather, the canvas would stiffen, making it even harder to raise or lower. The plastic rear windows would crack and turn yellow. Power tops appeared in the 1940s, making convertibles more practical. Electric or hydraulic motors did the heavy lifting, and latches became automatic. The driver just pressed a button and waited while the top raised or lowered itself. This made convertibles accessible to anyone, not just those with the strength and patience to wrestle with a manual top. Modern fabric tops are waterproof and insulated, solving most of the traditional convertible problems. Multiple layers of fabric, sound-deadening material, and proper seals make modern convertible tops nearly as quiet and weatherproof as fixed roofs. They last much longer than old canvas tops. Glass rear windows are standard. Some tops can even be lowered while driving at highway speeds. The convertible has evolved from a fair-weather vehicle into something practical year-round. Speedometers became common in the 1910s, but early versions were notoriously inaccurate. They used mechanical cables connected to the transmission or wheel. A flexible cable, similar to a modern speedometer cable, spun at a rate proportional to vehicle speed. This turned a magnet inside the speedometer, which dragged a needle against a spring. The faster the magnet spun, the farther it pulled the needle. Any slippage in the cable or wear in the gears would throw off the reading. Temperature changes affected the cable flexibility. If the cable kinked or got pinched during installation, it might not spin freely. Some speedometers were optimistic, reading higher than actual speed. This made cars seem faster than they were. Others were pessimistic, reading low. This could get you a speeding ticket, even when your speedometer showed you were within the limit. Drivers learned not to trust them completely. Experienced drivers would judge speed by engine sound, feel, and how fast landmarks passed. The speedometer was a rough guide at best. Calibration required special equipment and was rarely done. Even new speedometers could be off by 10% or more. This inaccuracy was just accepted as part of driving. Modern electronic speedometers are much more accurate, using wheel speed sensors or GPS data. They're typically within 1 or 2% of actual speed. Some are deliberately optimistic by a small amount to reduce the chance of speeding tickets. But even modern speedometers aren't perfect. Tire size changes from wear or replacement can affect accuracy, but they're far better than the mechanical speedometers they replaced. Oil pressure gauges were critical on early engines that had primitive lubrication systems. These engines used splash lubrication, where moving parts simply splashed oil around inside the crankcase. This wasn't very efficient, and oil pressure could drop dangerously low if oil level fell or the engine ran too hot. Without adequate oil pressure, bearings would fail in minutes or even seconds. Drivers had to watch the gauge constantly, particularly on long trips or in hot weather. A drop in oil pressure meant you needed to stop immediately and find out why. Maybe the oil level was low and just needed topping up. Maybe the engine was overheating and needed to cool down. Or maybe something had failed and the engine was about to destroy itself. The oil pressure gauge was your early warning system. Modern warning lights have replaced gauges in many cars, but enthusiasts still prefer gauges that show actual pressure rather than just a warning when pressure is already dangerously low. A gauge lets you see trends. If pressure gradually decreases over time, you know something is wearing out and needs attention soon. A warning light only tells you when the problem has already become serious. By then, damage may have already occurred. Some modern cars use dummy gauges that look like real gauges but actually just show normal or warning, with no real measurement in between. These fool owners into thinking they have real gauges while providing no more information than a warning light. Enthusiasts consider this deceptive, a cost-cutting measure disguised as proper instrumentation. Voltmeters show the electrical system voltage, indicating whether the generator or alternator is charging the battery properly. A healthy charging system should show around 14 volts when the engine is running. If the voltmeter shows 12 volts or less with the engine running, the charging system isn't working. The battery is powering everything, and it will go dead soon. 13.5 to 14.5 volts indicates proper charging. Many modern cars replace the voltmeter with a simple battery icon that illuminates if there's a problem. This is cheaper to manufacture and simpler for non-technical owners, but it provides no early warning. The warning light only comes on when the problem is already serious. A voltmeter shows gradual changes in charging voltage that indicate a problem is developing before complete failure occurs. Watching a voltmeter can also help diagnose electrical problems. If voltage drops when you turn on certain accessories, you know those accessories are drawing excessive current. If voltage is higher than normal, the voltage regulator might be failing, which can damage the battery and electrical components. A voltmeter provides useful information that a simple warning light cannot. Manifold vacuum gauges were popular in the 1970s and 1980s as fuel economy aids. Manifold vacuum is a suction created in the intake manifold when the throttle is mostly closed. Higher vacuum readings indicated efficient engine operation and light throttle. Lower vacuum meant you were accelerating hard or climbing a hill using more fuel. Drivers could use the gauge to modify their driving style for better economy. The gauge taught drivers to accelerate gently and maintain steady speeds. Watching the vacuum needle, you could learn to use the minimum throttle needed for any situation. This made a real difference in fuel economy, sometimes improving it by 10 or 20%. Skilled drivers could extract impressive mileage from cars that weren't particularly efficient by driving in a way that kept vacuum high. As fuel injection replaced carburetors and engines became more efficient, vacuum gauges disappeared from most vehicles. Modern engines with electronic throttle control and variable valve timing don't have the same direct relationship between manifold vacuum and fuel consumption. Fuel economy displays now show instant and average fuel consumption in miles per gallon or liters per 100 kilometers, providing similar information in a more direct way. Inclinometers show the angle of tilt, useful for off-road vehicles to indicate how steep a slope you're climbing or how much the vehicle is leaning in a side slope. Early inclinometers were simple devices with a ball bearing rolling along a curved scale or a bubble level in fluid. They showed tilt angle but weren't very precise. They didn't require power and couldn't fail electrically, but they were hard to read accurately, especially in a bouncing vehicle. Some luxury SUVs include digital inclinometers as part of their off-road information systems. These use electronic sensors to measure pitch and roll angles precisely. The display might show both front-to-back tilt and side-to-side lean simultaneously. Some systems include a compass and altitude reading, creating a comprehensive off-road information display. The graphics can be quite elaborate, showing a three-dimensional representation of the vehicle's orientation. Most owners never use them for their intended purpose. The inclinometer becomes just another interesting display to scroll through, occasionally amusing passengers, but rarely providing information that affects driving decisions. In serious off-road situations, experienced drivers judge angles by feel and visual reference rather than by looking at a gauge. But the inclinometer does provide bragging rights and looks impressive on the specification sheet. Studebaker began as a wagon manufacturer in 1852, building covered wagons for pioneers heading west across America. Brothers Henry and Clement Studebaker started making wheelbarrows and wagons in South Bend, Indiana. During the Civil War, they supplied wagons to the Union Army, which established their reputation for quality. After the war, Studebaker became one of America's largest wagon manufacturers. They built their first automobile in 1902, initially as a diversification move, while continuing to build wagons. As automobiles became more popular, Studebaker gradually shifted focus from wagons to cars. By 1920, they had stopped building wagons entirely, devoting all their production to automobiles. The transition from wagon maker to automobile manufacturer was remarkably successful for several decades. Studebaker became a significant manufacturer, building innovative and often stylish cars. They merged with Packard in 1954 in an attempt to create a stronger competitor to the big three automakers. However, neither brand survived. Packard production ended in 1958, and the last Studebaker was built in Canada in 1966. The company that had survived the transition from wagons to automobiles couldn't survive the competitive pressure from larger manufacturers. Their distinctive designs, particularly the bullet-nose models of 1950 to 1951, remain memorable. The bullet nose featured a chrome spinner in the center of the grille that looked like an aircraft propeller or bullet. It was either loved or hated, with no middle ground. Studebaker also built the beautiful Raymond Loewy design coupes of 1953 to 1964, which are still admired today. Despite some excellent designs, Studebaker couldn't achieve the sales volume needed to survive. Nash Motors introduced several innovations, including the first mass-produced car with seat belts as standard equipment in 1949. This was years before seat belts became common, let alone mandatory. Nash also offered a reclining front seat that converted into a bed, marketed as the Nash Airflight bed. This made the car appealing for travelers who wanted to sleep in their car rather than pay for a hotel. Nash introduced the first American compact car, the Rambler, in 1950. At a time when American cars were getting bigger and more powerful, the Rambler offered efficiency and practicality. Initially, it wasn't very successful, but when the economy turned down in the late 1950s, compact cars suddenly became attractive. Rambler sales soared, making it one of America's best-selling brands for a few years. Nash merged with Hudson to form American Motors Corporation in 1954. The Nash name disappeared from new cars after 1957, though the Rambler continued under the AMC banner. AMC survived as an independent manufacturer until being absorbed by Chrysler in 1987. Nash's legacy lived on to the Rambler name, and AMC's focus on smaller, more efficient vehicles. Hudson was known for step-down design in the late 1940s and early 1950s. Instead of sitting on top of the frame rails like most cars, the passenger compartment floor was lower than the frame. You literally stepped down into the car. This allowed lower overall height while maintaining headroom. It also lowered the center of gravity, improving handling significantly. This handling advantage was immediately apparent. Hudson Hornets dominated NASCAR in the early 1950s because of this handling advantage combined with powerful six-cylinder engine. From 1951 to 1954, Hudson's won more NASCAR races than any other manufacturer. The step-down design made them nearly unbeatable on the stock car circuit of the era. The step-down design was beautiful but expensive to build. The complex body structure required more labor than conventional designs. Hudson was a smaller manufacturer that couldn't afford the tooling cost to update the design frequently. By the mid-1950s, the step-down design was aging, and Hudson lacked the money to replace it. The merger with Nash formed AMC, but Hudson as a separate brand ended after 1957. Kaiser Frazer was an ambitious attempt to create a new American car company after World War II. Henry Kaiser, who had made a fortune building Liberty ships during the war, partnered with Joseph Frazer, an experienced automotive executive, to build cars. They purchased a massive government-built factory in Willow Run, Michigan, that had built B-24 bombers during the war. Kaiser Frazer achieved some success in the late 1940s when new cars were in short supply and demand was enormous. Their cars were unconventional, with front-wheel drive on some models years before it became common. They offered interesting features and styling. But as the Big Three ramped up production, Kaiser Frazer couldn't compete. Their production volumes were too low to achieve the economies of scale needed to match Big Three pricing. The company struggled through the early 1950s, building cars that were well-designed but expensive compared to Ford, Chevrolet, or Plymouth. The last Kaiser was built in 1955. The company continued building Jeeps, which they had acquired from Willis, for a few more years before selling the Jeep operation to AMC in 1970. Kaiser Frazer proved that building cars successfully required scale that new entrants couldn't achieve. DeSoto was Chrysler's mid-price brand, positioned between Plymouth and Dodge. Introduced in 1928, DeSoto was meant to capture buyers who wanted something better than Plymouth but couldn't afford a Chrysler. The strategy worked well for 3 decades. DeSoto sold well, offering distinctive styling and features that justified its price premium over Plymouth. By the late 1950s, the market for mid-price brands was shrinking. Buyers were either choosing economy cars or luxury cars, with less interest in the middle ground. All the mid-price brands suffered. Chrysler discontinued DeSoto in 1961 after selling over 2 million cars over 33 years. The 1961 models were essentially rebadged Chryslers, the result of cost-cutting as the brand wound down. Today, DeSotos are popular with collectors for their distinctive styling, particularly the models from the mid-1950s with their bold chrome grills and tail fins. The 1955 to 1956 DeSoto Fireflight is particularly sought after, with powerful V8 engines and stunning styling. The Adventurer model of 1956 was one of the fastest cars of its era. Though the brand is gone, DeSoto left behind some memorable automobiles. Disc brakes were developed for racing before appearing on road cars. The basic principle had been known for decades, but making it work reliably took time. Racing provided the incentive to solve the problems because the improved braking could mean the difference between winning and losing. Early disc brakes were temperamental, sensitive to heat, and required exotic materials. The Chrysler Imperial offered them in 1949, the first American production car with disc brakes. But the early design was problematic. The brakes worked well when cold, but faded badly when hot. The calipers would leak. Pad was excessive. Within a year, Chrysler discontinued them and went back to drum brakes. The technology wasn't ready for production use yet. British sports car makers adopted disc brakes in the 1950s with better results. Jaguar used disc brakes on their C-Type race cars with great success, then offered them on road-going XK models. The development work in racing had solved many of the earlier problems. By the 1960s, front disc brakes became common on performance cars, providing much better stopping power than drums. Rear disc brakes followed later as the technology matured. Today, disc brakes are universal on the front of every car and on all 4 wheels of most cars. They're more effective, provide better modulation, dissipate heat better, and are easier to service than drum brakes. Racing development proved the concept and worked out the problems before mass production adoption. It's a classic example of racing technology eventually benefiting everyday drivers. Ground effects in racing use the vehicle's underbody shape to create low pressure underneath, sucking the car toward the track. This provides downforce without the drag penalty of large wings. The concept revolutionized racing car design in the late 1970s. Lotus pioneered ground effects in Formula One, and their cars dominated for several seasons until other teams copied the technology. Ground effects cars had side pods shaped like inverted airfoils, with sealed skirts that touch the ground to maintain the low pressure underneath. As air flowed under these shaped tunnels, it accelerated, creating suction by the Bernoulli principle. The faster the car went, the more downforce it generated. This allowed cars to corner at incredible speeds. The technology worked too well. Cars became dangerously fast. If the skirts were damaged or lifted from the ground, the downforce disappeared instantly, often causing crashes. Formula One banned ground effects for safety reasons in 1983. However, the basic principles continue in modern race cars, which use carefully shaped underbodies to generate downforce without the extreme ground effect tunnels and skirts. Road cars occasionally incorporate ground effects principles on a much smaller scale. Ferrari, Porsche, and other sports car manufacturers use underbody aerodynamics to increase downforce. The effects are modest compared to race cars, but still improve high-speed stability. As computational fluid dynamics has improved, designing effective underbody aerodynamics has become easier, and more road cars benefit from these principles. Slick tires, with no tread pattern whatsoever, provide maximum grip on dry pavement. All the rubber contacts the road rather than having grooves that reduce contact area. The soft rubber compounds used in racing slicks become sticky when heated to operating temperature, creating enormous grip. Slicks are legal for street use, but universal in dry weather racing. In wet conditions, slicks are dangerous because they can't evacuate water and hydroplane easily. The development of tire compounds that work best at specific temperatures has become a critical part of racing strategy. Some compounds work best at lower temperatures, providing grip immediately but degrading quickly. Other compounds need higher temperatures to work but last longer. Choosing the right compound for the conditions and race length is crucial for success. Modern racing slicks are incredibly sophisticated. The rubber is formulated differently for different parts of the tire. The shoulder compound might be harder than the center to resist the extreme forces in corners. Temperature sensors inside the tires provide real-time data. Tire pressure must be set precisely because it affects both grip and wear. The simple-looking slick is actually a highly engineered component. Street performance tires incorporate some racing tire technology. Soft compound street tires in maximum performance categories provide impressive grip, though nothing like racing slicks. Some street-legal track tires are nearly slicks, with minimal tread depth just sufficient to meet legal requirements. These provide some of the performance of true slicks while being street-legal, though they wear quickly and are expensive. Telemetry systems allow racing teams to monitor hundreds of data points in real time as the car races. Engineers can see tire temperatures, brake temperatures, engine parameters, suspension movement, fuel consumption, and countless other measurements. This data streams wirelessly from the car to the pit, where engineers analyze it and communicate advice to the driver. The amount of data is staggering. Modern Formula One cars transmit gigabytes of data during each race. Every sensor is monitored continuously. Engineers can spot problems before they become failures. They can verify that the car is performing as expected. They can optimize strategy based on how the car is behaving. The driver may report that the car feels strange, and telemetry can show exactly what's wrong. Telemetry has changed racing strategy. Teams can monitor tire wear and performance, choosing pit stop timing to optimize advantage. Fuel consumption can be tracked precisely, allowing fuel savings when possible and full performance when needed. Brake temperatures might indicate that brake cooling ducts need adjustment. Every aspect of car performance can be optimized based on real data rather than guesswork. Some series restrict telemetry to keep costs down and increase driver importance. NASCAR limits telemetry, forcing teams to rely more on driver feedback. This keeps the racing closer and makes driver skill more important. But unrestricted series use every bit of telemetry available, pushing the technology constantly forward. Roll cages protect drivers in racing accidents by creating a strong structure around the driver. Early roll bars were simple hoops behind the driver's seat. They provided some protection if the car rolled over, but didn't protect against side impacts or frontal impacts. As racing speeds increased and crashes became more violent, simple roll bars proved inadequate. Modern roll cages are complex structures with tubes carefully placed to protect against impacts from any direction. The main hoop behind the driver connects the front bars extending toward the firewall, side bars protecting the doors, rear bars supporting the main hoop, and crossbars distributing impact loads. All these tubes must be precisely positioned and welded to create an integrated protective structure. Racing regulations specify roll cage construction in detail. Tube diameter, wall thickness, material, bending method, welding procedures. Everything is regulated to ensure adequate strength. Cages must be built by certified fabricators who understand both the regulations and the engineering principles. A poorly built cage might pass visual inspection but fail in a crash with potentially fatal results. Some street performance cars have roll cages for track use. However, roll cages in street cars create issues. The bars are hard and unforgiving. In a street accident, you might hit your head on the cage. Padding helps but isn't fully effective. Roll cages belong in dedicated race cars with drivers wearing helmets and proper restraints, not in street-driven vehicles. Wind tunnels allow engineers to study how air flows around vehicles without building full-size prototypes or testing on the road. Early automotive wind tunnels were crude affairs, often adapted from airplane wind tunnels. They couldn't accurately replicate real-world conditions. The car sat stationary while air blew over it, but this didn't perfectly simulate a car moving through still air. The boundary layer on the tunnel floor affected results. Modern facilities can simulate different speeds, crosswinds, and even rain. The most advanced tunnels have rolling road floors that move at the same speed as the simulated wind. This allows realistic testing of how air flows under the vehicle, which is critical for modern aerodynamic development. Some tunnels can vary temperature and altitude to simulate different conditions. Cars are tested at multiple wind angles to understand how they behave in crosswinds. Wind tunnel testing is expensive. Each hour of testing can cost thousands of dollars, but it's still cheaper than building multiple prototype vehicles and testing them on the road. Wind tunnels also allow testing in controlled, repeatable conditions. Road testing is affected by weather, traffic, and countless other variables. In the wind tunnel, you can isolate specific effects and understand exactly how changes affect performance. Computational fluid dynamics has supplemented wind tunnel testing in recent years. Computers can simulate airflow and predict how design changes will affect aerodynamics. This allows engineers to evaluate hundreds of variations before building anything physical. However, CFD isn't perfect. Wind tunnel testing remains essential to verify that computer predictions match reality and to catch unexpected effects that simulations might miss. Water channels use flowing water with dye to visualize airflow patterns. Water flows much slower than air but behaves similarly according to fluid dynamics principles. Engineers inject colored dye into the water flow and watch how it moves around scale models of vehicles. The dye makes flow patterns visible in ways that airflow cannot be seen. Engineers can see exactly where air separates from the vehicle surface, creating turbulent flow and drag. They can watch vortices form and understand where energy is being wasted. The visual nature of water channel testing makes it invaluable for understanding complex flow patterns. Many improvements in aerodynamics started with observations in water channels that suggested design changes, later verified in wind tunnels. Water channel testing uses scale models rather than full-size vehicles. The models must be precisely manufactured to match the proposed design. Even small imperfections can affect flow patterns. So models are often machined from solid blocks of material or 3D printed with great precision. Multiple models might be tested to evaluate different design variations. The beautiful thing about water channels is that you can literally see the problem and the solution. Acoustic wind tunnels measure wind noise, as well as aerodynamic forces. Microphones positioned throughout the tunnel pinpoint exactly where noise is generated. Is it the mirrors, the door seals, the windshield wipers, the A-pillar where the windshield meets the roof? Acoustic testing identifies the sources, so engineers can focus on the biggest noise contributors. Engineers can then modify mirror shapes, adjust door seal designs, change wiper designs, or alter body contours to reduce wind noise. Modern luxury cars are remarkably quiet at highway speeds thanks to acoustic testing. The reduction in noise isn't just for comfort. Lower noise levels reduce driver fatigue on long trips, making cars safer. What seems like a luxury feature actually has real safety benefits. Some acoustic tunnels use arrays of microphones and sophisticated software to create visual maps showing exactly where noise originates. These maps reveal problem areas that might not be obvious. A small gap or sharp edge that creates noise far out of proportion to its size can be identified and corrected. The level of detail in modern acoustic testing is remarkable. Climatic chambers expose vehicles to extreme temperatures, from far below zero to over 120 degrees Fahrenheit. Cars are started, driven on dynamometers, and tested in these conditions to ensure everything works properly. Does the engine start reliably in extreme cold? Do the door seals remain flexible? Does the air conditioning keep the cabin comfortable in extreme heat? Engineers test materials to verify they don't become brittle in cold or melt in heat. Electronics must function across the entire temperature range. Fluids must flow properly. Batteries must provide adequate power for starting. Even things like the fit of panels are checked as materials expand and contract with temperature changes. A car designed to sell globally must work in Alaska and Arizona, Norway and Nevada. Desert testing in places like Death Valley complements climatic chamber work, providing real-world validation of engineering. The intense heat and bright sunlight of the desert test cooling systems, air conditioning materials, and paint. Engineers drive cars for thousands of miles in these brutal conditions, looking for any problems that only appear with sustained exposure to extreme heat. What works in a climatic chamber for a few hours might fail in the desert after days of use. Cold weather testing in places like northern Alaska or Sweden tests starting, heating, and cold weather drivability. Extremely cold temperatures reveal problems that wouldn't appear in moderate climates. Does the transmission shift smoothly when the fluid is thick from cold? Do the brakes work before they warm up? Can you see clearly when snow and ice accumulate? Does the defroster work effectively? These real-world tests catch problems that laboratory testing might miss. Rough road testing facilities have surfaces with bumps, potholes, and various imperfections to test suspension durability and interior rattle resistance. Cars drive over these surfaces repeatedly, while engineers listen for squeaks and rattles. Accelerometers measure vibrations. Cameras record how panels and components move. The goal is to identify and eliminate any source of unwanted noise or vibration. Modern cars are remarkably rattle-free compared to cars from decades ago. This is the result of improved materials, better assembly techniques, and extensive testing. Engineers now understand how to isolate components, use proper fasteners, and design parts that don't buzz or rattle even after years of use. The quiet, solid feel of a modern car is no accident. It's the result of countless hours of testing and refinement. Some facilities have surfaces that simulate specific roads known to cause problems. If there's a particular rough road or bridge expansion joint that generates complaints, engineers can measure its characteristics and recreate it at the test facility. This allows them to reproduce the problem in a controlled environment, develop a solution, and verify the fix without repeatedly driving to the problem location. Durability testing drives cars over rough surfaces for hundreds of thousands of miles, equivalent to years of normal use compressed into months. Components are pushed to failure to identify weak points. Suspensions are cycled millions of times. The goal is to ensure that the car will hold up through years of normal use. If something is going to fail at 80,000 miles, better to discover that during development and fix it than have customers experience failures. The automobile has evolved in countless ways since those early days of tiller steering, wooden wheels, and brass fittings. Each generation has brought improvements, innovations, and occasionally ideas that didn't work quite as planned. But through it all, the essential character of the automobile has remained constant, a machine that provides freedom, independence, and the ability to travel wherever roads lead. The first automobile accident in history occurred in 1891 in Ohio. James William Lambert was driving one of his inventions when he hit a tree root, caused his car to swerve into a hitching post. Both Lambert and his passenger suffered minor injuries. This happened at a speed of probably less than 10 miles per hour. The first speeding ticket was issued in 1902 to a New York City taxi driver who was traveling at the breakneck speed of 12 miles per hour in a 5-mile-per-hour zone. The officer had to chase him down on a bicycle. Henry Ford did not invent the automobile, nor did he invent the assembly line. What he did invent was a moving assembly line for automobile production in 1913. This reduced the time to build a car from 12 hours to just 93 minutes. The Model T, which had cost $850 in 1908, dropped to just $260 by 1925. The Ford Model T was available in any color you wanted, as long as it was black. This wasn't a joke or marketing gimmick. Black paint dried faster than other colors, which was essential for the assembly line speed Ford wanted to achieve. By 1926, though, Ford began offering other colors as competitors were eating into his market share. Before cars had electric starters, you had to hand crank the engine to start it. This was dangerous. If the engine backfired, the crank could spin backwards and break your arm or wrist. Thousands of people were injured this way. The electric starter was invented by Charles Kettering in 1912 and first appeared in the 1912 Cadillac. It revolutionized driving, making it accessible to women and older individuals who couldn't safely hand crank an engine. The first car radio was invented in 1929 by two young men named William Lear and Elmer Wavering. They called their invention the Motorola, a combination of motor and Victrola. The radio cost $130, which was about one-third the cost of an entire car at the time. Despite the cost, it became incredibly popular because it gave people something to do during the long, boring drives of the era. Section 2, Engine Facts. The Boxer engine, also called a flat engine or horizontally opposed engine, is used by Subaru and Porsche. It's called a boxer engine because the pistons move in and out like boxers throwing punches. This design creates a lower center of gravity and better balance than traditional inline or V-configuration engines. The rotary engine, also known as the Wankel engine, has no pistons. Instead, it uses a triangular rotor that spins inside an oval-shaped chamber. Mazda is the only manufacturer that successfully mass-produced rotary engines. The RX-7 and RX-8 use this unique design. While smooth and high-revving, rotary engines are known for consuming oil and fuel and requiring frequent rebuilds. The most cylinders ever put in a production car engine is 16. The Bugatti Veyron uses a quad-turbocharged 8-liter W16 engine. This is essentially two V8 engines joined together. It produces over 1,000 horsepower and can push the car to speeds exceeding 250 miles per hour. Diesel engines don't use spark plugs. Instead, they compress air so much that it becomes hot enough to ignite the fuel. This compression ratio can be as high as 25-1, compared to about 10-1 in gasoline engines. This is why diesel engines are more efficient and produce more torque than gasoline engines. The term horsepower was coined by James Watt, the inventor of the steam engine. He calculated that a horse could do 33,000 foot-pounds of work per minute. 1 horsepower equals the ability to move 550 pounds 1 foot in 1 second. It's not a perfect comparison, and actual horses can produce more than 1 horsepower in short bursts. Turbochargers and superchargers both force more air into an engine, but they work differently. A turbocharger is powered by exhaust gases spinning a turbine. A supercharger is powered directly by the engine through a belt. Turbochargers are more efficient but have lag time. Superchargers provide instant boost but consume engine power to operate. Modern engines can run for 300,000 miles or more with proper maintenance. This is remarkable compared to engines from the 1960s and 70s, which often needed rebuilding by 100,000 miles. Better materials, tighter manufacturing tolerances, and improved lubricants have all contributed to this longevity. Section 3. Transmission Trivia. The first automatic transmission was invented in 1921 by a Canadian steam engineer named Alfred Horner Monroe. However, it wasn't until 1939 that General Motors introduced the first mass-produced automatic transmission, called the Hydra-Matic. It was available in the 1940 Oldsmobile. Manual transmissions are more efficient than automatics, but this gap has closed significantly. Modern automatic transmissions with 8, 9, or even 10 speeds can match or exceed the fuel economy of manuals. Continuously variable transmissions, or CVTs, can be even more efficient because they don't have fixed gear ratios. The clutch in a manual transmission uses friction to connect the engine to the transmission. It's made of materials similar to brake pads. A typical clutch can last anywhere from 30,000 to 150,000 miles, depending on driving style. Riding the clutch or slipping it excessively generates heat and wears it out faster. Double clutching is a technique where you shift to neutral, release the clutch, rev the engine to match the speed of the next gear, then shift into gear. This was necessary for old transmissions that didn't have synchronizers. Today's transmissions have synchros that match the gear speeds automatically, making double clutching unnecessary, except in heavy trucks or racing. The dual clutch transmission combines the efficiency of a manual with the convenience of an automatic. It uses two separate clutches, one for odd gears and one for even gears. While you're driving in third gear, the transmission preselects fourth gear, so the shift happens almost instantaneously. Volkswagen, Porsche, and other European manufacturers favor this design. Continuously variable transmissions use a belt or chain running between two variable diameter pulleys. By changing the diameter ratio between the pulleys, they can provide infinite gear ratios within their operating range. This allows the engine to run at its most efficient RPM regardless of vehicle speed. However, many drivers dislike the feel because there's no traditional shift sensation. The parking pawl is a small metal pin that locks your transmission when you put in park. It engages with a notch wheel connected to the transmission output shaft. If you park on a steep hill without using the parking brake, all the weight of the car rests on this small pin. Always use your parking brake to take the load off the parking pawl. Section 4. Brake and Tire Knowledge. Anti-lock brakes, or ABS, prevent your wheels from locking up during hard braking. They do this by rapidly pulsing the brakes, sometimes over 15 times per second. This maintains steering control and reduces stopping distance on most surfaces. The system was adapted from aircraft landing gear in the 1970s. Brake fluid is hygroscopic, which means it absorbs moisture from the air. Over time, this moisture lowers the boiling point of the brake fluid. If your brake fluid boils during hard braking, it creates air bubbles that compress, causing brake fade or complete brake failure. This is why brake fluid should be changed every 2 to 3 years. The first pneumatic tire was invented in 1888 by John Boyd Dunlop for his son's tricycle. Before this, vehicles used solid rubber tires that provide a harsh, uncomfortable ride. The air-filled tire revolutionized transportation by providing cushioning and better traction. Tire pressure increases as tires heat up from driving. A tire that's properly inflated when cold can gain 3 to 5 psi after driving for 20 minutes. This is normal and expected. Always check tire pressure when tires are cold for accurate readings. The numbers on your tire sidewall tell you everything about the tire. For example, 205/55 or 16 means the tire is 205 millimeters wide. The sidewall height is 55% of the width, or means radial construction, and 16 is the wheel diameter in inches. Tire tread is designed to channel water away from the contact patch. The grooves and sipes in the tread create paths for water to escape, preventing hydroplaning. This is why tire tread depth is critical for wet weather safety. Most states require at least 2 30-seconds of an inch of tread depth, but 3 30-seconds is much safer. Nitrogen in tires is used primarily in racing and aircraft. The main benefit is that nitrogen molecules are larger than oxygen molecules, so they leak out more slowly. Nitrogen also doesn't contain moisture. For normal driving, the benefits are minimal, and regular air works just fine if you check pressure monthly. Section 5. Fuel and Combustion. Gasoline is a mixture of hundreds of different hydrocarbons refined from crude oil. The octane rating indicates the fuel's resistance to knocking or pre-ignition. Higher octane doesn't mean more power, unless your engine is designed to take advantage of it. Using premium fuel in a car designed for regular is just wasting money. NOx sensors in modern engines listen for pre-ignition or detonation. If they detect knocking, they retard the ignition timing to prevent engine damage. This is why modern engines can run on lower octane fuel than they're designed for, though with reduced performance and efficiency. The air-fuel ratio for optimal combustion is about 14.7 to 1 by weight. This is called stoichiometric ratio. Engines run richer than this for more power or leaner for better fuel economy. But 14.7 to 1 provides complete combustion with minimal emissions. Fuel injectors spray fuel in a fine mist to mix with incoming air. They operate at pressures between 30 and 80 psi in port injection systems. Direct injection systems operate at over 2,000 psi. This high pressure creates an extremely fine mist that burns more completely. The catalytic converter uses precious metals like platinum, palladium, and rhodium to convert harmful emissions into less harmful substances. It turns carbon monoxide into carbon dioxide, hydrocarbons into carbon dioxide and water, and nitrogen oxides into nitrogen and oxygen. This is why catalytic converters are targets for thieves. The metals inside are valuable. Ethanol is added to gasoline in many regions, typically at 10% concentration called E10. Ethanol contains less energy than gasoline, so it slightly reduces fuel economy. It also attracts water and can damage certain rubber and plastic components in older vehicles. However, it burns cleaner and is renewable. Diesel fuel contains more energy per gallon than gasoline. This is why diesel vehicles typically get better fuel economy. Diesel also acts as a lubricant for the fuel injection system, unlike gasoline. Using gasoline in a diesel engine would star the injection pump lubrication and cause catastrophic damage. Section 6. Electrical Systems. The battery in your car is a lead-acid battery, the same basic design that's been used for over 100 years. It consists of lead plates suspended in sulfuric acid. Chemical reactions create and store electrical energy. A typical car battery provides 12.6 volts when fully charged. The alternator generates electricity while the engine runs. It's called an alternator because it produces alternating current, which is then converted to direct current to charge a battery and power the vehicle's electrical systems. Early cars used DC generators, but alternators are lighter, more efficient, and more reliable. Your car's electrical system operates on direct current at 12 volts, but the alternator produces alternating current at varying voltages. The voltage regulator ensures the charging voltage stays between 13.5 and 14.5 volts to properly charge a battery without overcharging it. Spark plugs create an electrical arc that ignites the air-fuel mixture. This spark can be up to 40,000 volts in modern ignition systems. The spark jumps a gap of around 1 millimeter in about 1/10,000th of a second. Spark plugs fire millions of times over their lifetime. The ignition coil transforms the battery's 12 volts into the thousands of volts needed for the spark plug. Modern cars have coil-on plug systems where each spark plug has its own dedicated coil. Older cars use a single coil and distributor to send high voltage to each spark plug in sequence. The computer in your car, called the Engine Control Unit or ECU, monitors hundreds of sensors and makes millions of calculations per second. It controls fuel injection, ignition timing, emission systems, and countless other functions. Modern luxury cars can have over 100 computers controlling everything from the engine to the seat heaters. The oxygen sensor in your exhaust measures the amount of oxygen in the exhaust gases. This tells the computer if the engine is running rich or lean, allowing it to adjust the fuel mixture for optimal efficiency and emissions. Modern cars have multiple oxygen sensors for precise control. Section 7. Cooling and lubrication. Engine coolant, also called antifreeze, serves multiple purposes. It prevents the coolant from freezing in winter and boiling in summer. It also contains corrosion inhibitors to protect the metal components in the cooling system. A 50-50 mix of coolant and water provides protection to about -34 degrees Fahrenheit. The thermostat is a simple mechanical valve that stays closed when the engine is cold and opens when it reaches operating temperature. This allows the engine to warm up quickly for better efficiency and emissions. Most engines operate between 180 and 210 degrees Fahrenheit. The water pump circulates coolant through the engine and radiator. It's typically driven by the serpentine belt or timing belt. When water pumps fail, they can leak coolant or make a grinding noise. Some engines have electric water pumps that can vary their speed based on cooling needs. Radiators transfer heat from the hot coolant to the air flowing through them. They consist of thin metal tubes surrounded by fins to maximize surface area. The radiator cap maintains pressure in the cooling system, which raises the boiling point of the coolant. A 15 psi radiator cap raises the boiling point to about 260 degrees Fahrenheit. Motor oil does more than just lubricate. It also helps cool the engine by carrying heat away from moving parts. It cleans by suspending dirt and combustion byproducts. It seals the small gaps between pistons and cylinder walls. And it protects against corrosion. Modern synthetic oils do all these jobs better than conventional oils. The viscosity rating of oil, like 5W30, tells you how thick the oil is. The W stands for winter. 5W means the oil flows like a 5-weight oil when cold. 30 means it flows like a 30-weight oil when hot. Multi-viscosity oils use additives that change behavior with temperature. The oil filter traps particles and contaminants as oil circulates through the engine. It contains filter media that can trap particles as small as 20 to 30 microns. The filter has a bypass valve that opens if the filter becomes clogged, allowing unfiltered oil to flow rather than starving the engine of lubrication. Section 8. Aerodynamics and Design. The coefficient of drag, or CD, measures how aerodynamic a vehicle is. A lower number means less air resistance. A typical modern sedan has a CD of around 0.3. The most aerodynamic production car, the Mercedes EQS, has a CD of just 0.2. By comparison, a brick has a CD of around 2.1. Aerodynamic drag increases with the square of speed. This means that doubling your speed quadruples the air resistance. This is why fuel economy drops significantly at highway speeds above 65 miles per hour. The engine has to work much harder to push through the air. Downforce is negative lift. Race cars use wings and underbody designs to create downforce, pushing the car onto the track for better grip at high speeds. The trade-off is increased drag, which reduces top speed. Race teams carefully balance downforce and drag for each track. The crumple zones in modern cars are designed to form in a controlled manner during a crash. This extends the time of the collision, reducing the peak forces experienced by occupants. The passenger compartment, however, is a rigid safety cell designed not to deform. This combination saves lives. Side mirrors create significant aerodynamic drag. This is why many modern cars have smaller mirrors, or even replace them with cameras. Removing side mirrors can improve fuel economy by up to 2% at highway speeds. The grille on a car isn't just for looks. It allows air to flow to the radiator for cooling. However, modern efficient engines don't need as much cooling. So many new cars have active grille shutters that close at highway speeds to reduce drag and improve aerodynamics. Underbody panels smooth the airflow into the car, reducing drag and improving fuel economy. Race cars take this to the extreme with completely flat underbodies. Production cars compromise between aerodynamics, cost, and the need to access components for service. Section 9. Safety Features. Seat belts save more lives than any other safety feature. The 3-point seat belt, which crosses your lap and shoulder, was invented by Volvo engineer Nils Bohlin in 1959. Volvo made the patent open and available to other manufacturers because they considered it too important to keep to themselves. Airbags deploy at speeds up to 200 miles per hour. They fully inflate in about 30 to 40 milliseconds. That's faster than you can blink. Sensors detect the deceleration of a crash and trigger the airbags before you've even moved forward in your seat. Modern cars have multiple airbags. Front airbags for driver and passenger, side airbags and seats, curtain airbags along the roof, and even knee airbags. High-end luxury cars can have 10 or more airbags. Each one is designed to protect specific body parts in different types of crashes. Electronic stability control uses individual wheel braking and sometimes engine power reduction to help keep the car under control. If the system detects that the car is starting to slide or spin, it intervenes automatically. This technology has prevented countless accidents and is now mandatory on all new cars. Collision avoidance systems use radar, LiDAR, or cameras to detect obstacles and potential collisions. They can warn the driver, apply the brakes automatically, or even steer to avoid a crash. These systems are becoming standard equipment on most new vehicles. Backup cameras became mandatory on all new cars sold in the United States in 2018. They significantly reduce backing accidents, especially those involving children who are too short to be seen in mirrors. The camera must activate whenever the vehicle is put in reverse. Crumple zones, airbags, and seatbelts work together. The crumple zones extend the collision time. The seatbelt restrains you and prevents ejection. The airbags cushion the impact. Each system depends on the others working properly. This is why it's critical to replace airbags after deployment and fix collision damage properly. Section 10. Manufacturing and Materials. Modern cars are assembled from thousands of individual parts. A typical car contains about 30,000 components. The supply chain required to manufacture cars is incredibly complex, with parts coming from suppliers all over the world. The body of most cars is made from steel, but aluminum is increasingly common to reduce weight. Some exotic cars use carbon fiber, which is extremely strong and light, but also expensive. The Honda NSX was the first production car with an all-aluminum body, introduced in 1990. High-strength steel allows manufacturers to make thinner, lighter parts that are still strong enough for crash protection. Advanced high-strength steels can be 3 times stronger than regular steel. This strength-to-weight improvement is critical for fuel economy and safety. Robots do most of the welding in modern car factories. A typical car body can have over 4,000 weld points. Robots can place these welds with perfect consistency and precision, which is important for structural integrity and crash performance. Paint isn't just for appearance. It protects the metal from corrosion. Modern car paint is applied in multiple layers: primer, base coat, and clear coat. The entire process takes place in carefully controlled environments to prevent dust and defects. The clear coat provides UV protection and gloss. Galvanizing is a process where steel is coated with zinc to prevent rust. Many modern cars use galvanized steel for body panels, which is why rust-through is much less common than it was decades ago. Some manufacturers offer rust-through warranties of 10 years or longer. Quality control in car manufacturing includes both automated checking and human inspection. Cars are tested on dynamometers, water tested for leaks, and driven through rough surfaces to detect squeaks and rattles. A small percentage of cars are taken completely apart to verify that assembly was done correctly. Section 11. Unusual and interesting facts. The average car contains about 25,000 pounds of materials. This includes steel, aluminum, plastic, rubber, glass, and various fluids. About 75% of a car by weight can be recycled at the end of its life. Car keys have evolved from simple metal keys to electronic fobs that communicate with the car. Modern keyless entry systems use encrypted radio signals. Some high-end cars use proximity sensing, where the car unlocks automatically when you approach with the key fob in your pocket. The new car smell that people find pleasant is actually the smell of volatile organic compounds off-gassing from plastics, adhesives, and upholstery. Manufacturers work to minimize these emissions because some compounds can be harmful in high concentrations. The smell fades as materials age and off-gassing decreases. The average American spends about 54 minutes per day driving. That's over 330 hours per year, or almost 14 full days behind the wheel. Over a lifetime, the average person will spend over 2 years inside their car. Windshield wipers were invented by Mary Anderson in 1903 after she noticed streetcar drivers had to open their windows in the rain to see. Her design was initially rejected by manufacturers who thought it would distract drivers, but it became standard equipment within a decade. Cruise control was invented by a blind man named Ralph Teeter in 1948. The story goes that he was frustrated by his lawyer's habit of speeding up and slowing down while talking. Teeter's mechanical cruise control maintained steady speed using centrifugal force and throttle position. The roads you drive on are designed with specific slopes for drainage. Roads are crowned in the center, so water runs the sides. Curves are banked to help vehicles maintain grip while turning. The engineering that goes into road design is surprisingly complex. Section 12. Electrical and hybrid vehicles. Electric vehicles aren't new. In fact, Electric cars were popular in the early 1900s, before gasoline cars became dominant. They were quieter, cleaner, and easier to operate than gasoline cars. The development of the electric starter and cheap gasoline led to their decline. Modern electric vehicles use lithium-ion batteries, the same technology in your laptop and phone, but scaled up massively. A Tesla Model S battery pack contains over 7,000 individual cells. These batteries can store around 100 kilowatt-hours of energy, enough to power the average house for about 3 days. Regenerative braking in electric and hybrid vehicles captures the energy normally lost as heat during braking. The electric motor runs in reverse, acting as a generator to charge the battery. This improves efficiency by 10 to 25% in city driving. Hybrid vehicles combine a gasoline engine with an electric motor and battery. The electric motor can power the car alone at low speeds, assist the engine during acceleration, or capture energy during braking. The engine can run at its most efficient RPM or shut off completely when not needed. Electric motors produce maximum torque from 0 RPM. This is why electric vehicles accelerate so quickly. A gasoline engine has to build RPM to produce power, but an electric motor delivers full torque instantly. This instant response makes electric vehicles feel very quick even if their top speed is limited. Charging an electric vehicle takes longer than filling a gas tank, but most charging happens at home overnight. A typical 240-volt home charger can fully charge an electric vehicle in 4 to 8 hours. Fast public chargers can add 200 miles of range in 20 to 30 minutes. The range anxiety people feel about electric vehicles is becoming less of an issue as battery technology improves. Many modern electric vehicles can travel over 300 miles on a charge, which exceeds most people's daily driving needs. For longer trips, fast charging networks are expanding rapidly. Section 13. Racing and Performance. Formula One cars can pull lateral G-forces of up to 6 GS in corners. That's 6 times the force of gravity pressing the driver into the seat. The human body can only withstand this because of specialized training and because the forces are distributed across the body by the seat and harness. The engines in modern Formula One cars are 1.6-liter turbocharged V6s, yet they produce over 1,000 horsepower. They rev to 15,000 RPM and are among the most thermally efficient engines ever created, converting over 50% of fuel energy into mechanical work. Drag racing vehicles can accelerate so quickly that drivers experience over 5 GS. Top fuel dragsters reach over 330 miles per hour in less than 4 seconds, covering a quarter mile. The supercharged engines produce over 11,000 horsepower and consume about 15 gallons of nitromethane fuel per run. NASCAR vehicles look like stock cars but share very little with production vehicles. They use tube-frame chassis, carbureted V8 engines, and 4-speed manual transmissions. The body panels are shaped to match production cars, but are purpose-built for racing. Endurance racing, like the 24 Hours of Le Mans, tests reliability as much as speed. Cars must run at racing speeds for a full day with minimal maintenance. Manufacturers use these races to prove the durability of their technology. The Nürburgring Nordschleife in Germany is considered the ultimate test of a performance car. The track is 12.9 miles long with over 150 turns and significant elevation changes. Manufacturers use lap times at the Nürburgring as a benchmark for performance. Section 14. The future of cars. Autonomous vehicles use a combination of sensors to navigate. These include cameras for visual information, radar for detecting objects and measuring distance, LiDAR for creating three-dimensional maps, and GPS for positioning. The computer processes all this data to make driving decisions. Self-driving technology is categorized into levels from 0 to 5. Level 0 is no automation. Level 1 is basic features like cruise control. Level 2 includes systems like Tesla Autopilot that can steer and control speed but require driver monitoring. Level 5 will be full automation with no human input required. Connected car technology allows vehicles to communicate with each other and with infrastructure. Cars will warn each other about hazards, coordinate to reduce traffic congestion, or receive updates about traffic lights and road conditions. This vehicle-to-everything communication could significantly improve safety and efficiency. Hydrogen fuel cell vehicles generate electricity through a chemical reaction between hydrogen and oxygen. The only byproduct is water vapor. They can refuel in minutes like gasoline cars, but offer the efficiency and smoothness of electric vehicles. The main challenges are the cost of fuel cells and the lack of hydrogen refueling infrastructure. Three-dimensional printing is starting to be used in car manufacturing. It allows for complex shapes that would be difficult or impossible with traditional manufacturing. Some companies are printing entire car bodies or chassis in a single piece. As the technology improves, it could revolutionize how cars are designed and built. Biofuels made from plants can be used in existing gasoline and diesel engines with little or no modification. Ethanol and biodiesel are already in use. Advanced biofuels could be carbon neutral, as the carbon released when burning them was recently absorbed from the atmosphere by the plants. Section 15, Maintenance Wisdom. Regular oil changes are the single most important maintenance task for engine longevity. Oil lubricates moving parts, cleans contaminants, and helps cool the engine. As it ages, it breaks down and becomes less effective. Fresh oil keeps engines running smoothly for hundreds of thousands of miles. Tire rotation extends tire life by ensuring even wear. Front tires typically wear faster than rear tires because they handle steering and most of the braking. Rotating tires every 5,000 to 7,000 miles distributes the wear evenly across all four tires. Transmission fluid doesn't last forever, despite what some manufacturers claim. It breaks down over time and becomes contaminated with metal particles from wear. Regular transmission fluid changes can extend transmission life significantly. Most transmissions benefit from fluid changes every 30,000 to 60,000 miles. Air filters are simple but important. A clogged air filter restricts airflow to the engine, reducing power and fuel economy. Replacing the air filter is one of the easiest maintenance tasks you can do yourself and only takes a few minutes. Brake fluid absorbs moisture over time, which lowers its boiling point and can lead to brake fade or failure. Flushing brake fluid every 2 to 3 years maintains braking performance and prevents corrosion in the brake system. Coolant contains additives that prevent corrosion and maintain proper pH. These additives deplete over time, even though the coolant itself doesn't wear out. Regular coolant changes protect your engine and cooling system components from corrosion and damage. Battery terminals can corrode, creating resistance that prevents proper charging. Cleaning battery terminals and keeping them protected with a corrosion inhibitor ensures reliable starting and proper charging system function. Section 16, Closing Thoughts. Cars represent freedom and independence. They allow us to travel where we want, when we want. They've shaped our cities, our culture, and our economy. The personal automobile has been one of the most transformative technologies of the modern era. From the first horseless carriages to today's electric and autonomous vehicles, cars have continuously evolved. Each generation of technology has brought improvements in safety, efficiency, and capability. The cars of tomorrow will be cleaner, safer, and more connected than anything we drive today. The internal combustion engine has powered our world for over a century. While its era may be coming to an end, its impact will be felt for generations. The engineering lessons learned and the infrastructure built around it have shaped modern civilization. Maintaining a car is about more than just keeping it running. It's about taking care of something that takes care of you. A well-maintained vehicle is reliable, safe, and can last for decades. The time and money invested in maintenance is always less than the cost of neglect. Every car has a story. The memories of road trips, daily commutes, first dates, bringing home new babies. Cars are more than just transportation. They're part of our lives, witnesses to our journeys. As you drift off to sleep, perhaps you're thinking about your own car, or a car you once loved, or a dream car you hope to own someday. Whatever the case, rest peacefully knowing that these machines, these remarkable combinations of metal and engineering and human ingenuity, will be there tomorrow, ready to take you wherever you need to go. Sleep well, drive safely, and may your journeys always be smooth. Good night.